Hi, this is Elliot Fishman, and welcome to part 3 of the future of imaging pancreatic cancer, from cinematic rendering to radiomics to deep learning. And on the first two talks, we spoke about cinematic rendering, then a little bit about cinematic rendering, including HoloLens, and then we did radiomics. And now let's get into what we've been doing with deep learning. So for the past 5 years, we've had the Felix Project, and basically this was a project that combined the resources of computer science at Homewood, radiology, oncology, pathology at Johns Hopkins. And here's how it kind of looked. We had software from Variant Velocity for doing image segmentation. We had 5 Velocity workstations. We had 4 computing workstations also available at the undergraduate campus. There were another 18 computing workstations. We had NVIDIA supercomputers. We had 2 of the DGX-1s with over 200 terabytes of storage in each of the systems. What we first did, we looked at normal patients, normal renal donors, to be able to see, could we teach the computer to be able to recognize individual structures, liver, spleen, bowel, and particularly pancreas. So we segmented everything in arterial and venous display. Here's a typical example, 3 to 4 hours a case, teaching the computer everything you wanted to know about the body and drawing it. We had 4 different or 5 different people, depending, who drew the images or labeled the images, and then one of 3 of us then checked it. So lots of work went into that. And it was a 3D model in a sense. And after about a year, it got to the point where here's the image, here's the manual segmentation, that means it's one of us, and there was the computer prediction. So the computer prediction was literally one-to-one with us in predicting and recognizing individual organs. An example here is the pancreas in the image, annotation is us, and the prediction is the computer model. Again, very nicely one-to-one correlation. And even in this case, we have the patient's portal vein, splenic vein confluence, which you recognize with the pancreas. The computer recognized it, as did our annotators. Again, one-to-one. So then we said, okay, now we could recognize the pancreas, the various organs. What about pancreatic cancer? Just because you can find the pancreas and draw it accurately doesn't mean you can recognize pancreatic cancer. So the next couple of years we spent developing algorithms that would allow us to detect the presence of pancreatic cancer. And we tried to develop the algorithms very much as if a radiologist was reading it. We use visual cues for detecting pancreatic cancer: abnormal shape, changes in attenuation and texture, abrupt transition in the pancreatic duct or dilatation of the common duct. We look at peripancreatic vascular involvement. And we use this expert knowledge to help design what we do, but also we wanted that expert knowledge to help design the deep network to be able to recognize the tumor. Jensen Wang makes the point, when you do driverless cars, you're not teaching a computer to drive a car, you're trying to teach a computer to think like a person who's driving a car. Think about the millions of decisions you make when you're driving, when to speed up, when to slow down, how to behave when it's raining out or snowing out or it's sunny out. You need to teach the computer to do all of those features and do them like a person if you want the computer to be able to succeed at its task. And so we labeled several thousand pancreatic cancers. You can see one example here. And again, taught the computer how to recognize what's tumor versus not tumor. We taught it to recognize neuroendocrine tumors, recognize cysts. And again, detection is step number 1. And then once you have detection, then it's classification that becomes very important. We developed many different computer algorithms. Coarse-defined pancreatic detection was one of the algorithms for being able to recognize the pancreas and draw in the pancreatic bodies. We recognize all this information with shape. We developed a recurrentsaliency transformation network. The coarse segmentation stage is connected to the fine segmentation stage via transformation layer. The coarse and fine segmentation networks can be optimized jointly, and the coarse segmentation can mask can help the fine segmentation. And we use this as a way of localizing the gland defining the boundaries of the gland, and then detecting tumor, whether it's totally in the gland or extending beyond the gland. And here's just a simple, or maybe it's not simple, of a visualization of how the recurrent saliency network works in course-defined segmentation. And again, you'll note that the 3 weight maps capture different visual cues, with 2 of them focused on the foreground region and the remaining one focused on the background. And so when you look at how well we can do, look at this set of images here, mass in the body of the pancreas, dilated duct. That's the deep network prediction. Look how nicely it shows the tumor in red, turquoise for the pancreatic duct, and the remaining pancreatic gland in blue. You can see it very nicely that not only does it detect the tumor and the gland and the duct, but doesn't spill out. So it's really very specific what it's looking at. That's impressive. Or in this example, showing 3 different cases that we're not just picking up large tumors, but we're able to pick up small tumors with a sensitivity and specificity of over 90%. Here's another example. Here's a patient where you look at the image, and let's take you through it. And you're scrolling through the image, you can see the label, which is us. You can see the information based on the single phase acquisition and the information based on the dual phase acquisition. One of the things we've been looking at is doing the images both with single phase and using the dual phase data. The question will be which is better, but the computer will help us decide that, and that's what we'll specifically do. And here's just another example in arterial phase. Tumor in red, blue is the gland, purple is the duct. Just very nice visualizations with high dice scores. And again, another example here on venous phase imaging of the ability to detect the tumor in the head of the pancreas, see the dilated pancreatic duct, and then see the normal gland. All of it, when the labelers do it, which is us versus the computer, the accuracy is 1-to-1. So a very, very important set of images to really tell you precisely where we stand. Now for smaller tumors, which is going to be the key, beautiful example of a 1.5 centimeter lesion picked up, manual segmentation and the deep network, equally good. Or in this case, another small tumor in the neck of the pancreas, and near the head, 1.4 centimeters. You see the pancreatic duct, you nicely see the tumor, both on the manual segmentation and on the deep network prediction. And here's a third one, dilated pancreatic duct. You have a small tumor causing duct obstruction, but the tumor is recognized because the algorithm is trained on the pancreatic duct and to look for transitions where the duct gets cut off. And again, the importance of being able to think like a radiologist. Remember, we keep telling you, look for a duct. If you see a dilated duct, there's got to be a cancer. Well, here the computer will look. It finds the dilated duct, tracks the duct, and at the site of duct transition or cutoff, you see a mass present in both of these examples. So again, very, very important. When you look at this multi-scale course-defined segmentation for screening for pancreatic ductal adenocarcinoma, sensitivity 94%, specificity 98%. So again, very, very important. And here's one of the articles by Yang Wang and the team, Learning Inductive Attention Guidance for Partial Supervised Pancreatic Ductal Adenocarcinoma Prediction. And again, looking at what we can do, that the guidance is inductive, which not only provides bag-level pseudo-labels to training data without provoxal annotations for MIL training, but also acts as a proxy of an instant-level classifier. So again, very, very important, and our results are indeed very good. And here's just one of the examples of showing you some smaller tumors. Now the computer can recognize the pancreas, create the 3D model, and thus show you precisely where the tumor is. And again, here's the architecture. The architecture keeps changing, keeps evolving, but it's being trained with more data, more problematic data, smaller cases, trained not only with pancreatic adenocarcinoma, but neuroendocrine tumors and a range of cystic lesions, and trying to have it learn all of this information. In this paper, the paper addresses the problem of predicting pancreatic adenocarcinoma, this inductive attention guidance strategy for learning a global image level classifier, and a local instance level classifier for semi-supervised pancreatic adenocarcinoma segmentation will have certain specific advantages. So I think at Hopkins and many other institutions, there's a lot of work going on in pancreatic cancer, trying to find the best system which to do things. And so our goal, and the goal, you can look at this chart, look at the chart for a second, and what you can see very nicely on the chart, our goal is to combine deep learning with radiomics, because we think that the radiomics is very good for detecting disease, deep learning very good for finding it. Well, what if you combine both of them? Will this increase your accuracy substantially? Would we be able to use the random forest and the deep learning models together for tumor localization and prediction? And I think then other visualization techniques can be used as well. And this potential workflow needs to be done where it's transparent to the user, but it's easy to use for the user and allows us to be able to predict what the patient's outcomes are going to be. Now, once you have detection and you get that very good, then you're going to want to think about what else can you do with the data. If you go beyond even pancreatic cancer to CIS, what about predicting whether or not lesion is malignant? Is it low-grade dysplasia or high-grade dysplasia? And if it's a pancreatic cancer, what about survival? All of those things we spoke about are things we want to look at. Now, this was an article published by the group at Hopkins looking at pancreatic cystic lesions that were concerning for tumors. And what this article did was use computer algorithms to help predict whether or not you could predict better the management of patients with pancreatic cystic lesions. And this was called the ComCys test. It was a test based on selected clinical features, imaging characteristics, and cyst fluid genetic and biochemical markers. Using data from 436 patients with pancreatic cyst, they trained the ComCys to classify patients who would require surgery, those who should be routinely monitored, and those that did not require surveillance. The ComCys was more accurate than conventional clinical and imaging criteria alone, and so the conclusion, of course, in 2019, it had the potential to reduce patient morbidity and economic costs. Well, when you look at that article, you can see it did much better than physicians did, surgeons or GI docs, but it really wasn't as accurate as you would like it to be. It was probably in the 60% range when all was said and done. Well, can you do better than this? Well, what we did then, working with Microsoft and the Microsoft AI for Healthcare, looking at whether newer algorithms, remember this article is published in 2019, the work is done 2017, 2018. Well, what about some of the newer techniques? And working with Juan Ferez and his team, I think we have very exciting news. What they did, when they look at the data, they use interpretml, which is an open source Python package, which does several things that's very important. We always complain about AI that it's a black box. You give the data, it comes to an answer which may be very good, but you don't know why. Well, with this imaging technique, with this computer technique, it's more of a glass box. You can see precisely why the computer makes the decisions it does, and then you can change the parameters and see the impact of changing those parameters on the final outcome. One of the things about interpretml also includes the first implementation of the explainable boosting machine, a powerful interpretable glass box model that can be as accurate as many black box models. And here's just the architecture, but what makes it very exciting even conceptually is everyone is afraid of the black box. The glass box is what we want to see. We want to know how decisions are made and how we can improve decisions. If you have a black box, it's hard to figure out how to improve things. With a transparent or glass box system, you could improve things. As part of the network, interpretml also includes a new interpretable algorithm. I mentioned that, but this glass box model is just so important to us. And this article by Nori really is worth reading on your free time. These EBMs are highly intelligible because the contribution of each feature to a final prediction can be visualized and understood on plotting. And so, for example, what happens is when we look at, in this case, looking at age as a function, one of the things you look at when you're doing predictions is you have all of the parameters on the right, and you can see what impacts specifically the prediction. In many ways, we're using a multi-class approach to making decisions as to discharge, monitor, or have surgery. It's very much, I won't say binary, but it is binary. You're trying to make very specific decisions. Operate or simply follow or simply discharge. So in some ways it's operate, not operate, but under the not operate, there's two decisions: continue to follow or simply discharge. And the work we're looking at, the preliminary work, shows very nicely the ability to segment out the various tumor types, recognize and manage the patients specifically for every different tumor type, and again, the ability to have really high accuracy. And in many ways, what we're talking about here are GAMs, which is a class of statistical models in which the usual linear relationship between response and predictors are replaced by several nonlinear smooth functions to model and capture the nonlinearities of the data. Oh boy, I screwed up that word. Nonlinearities. Ooh, what a word, what a word. Anyway, you can see here's some of the preliminary work on IPMNs. Look how high the AUC is in predicting, and you can see the features which help predict exactly what the lesion is and whether or not the lesion should be managed conservatively or with surgery. And the same thing is true with pancreatic cancer, looking at parameters, looking at outcomes, or serous cystic neoplasms. All of the things very, very exciting. Now, all of these tools are coming together at a perfect time. This recent article by Tashima, Focal Pancreatic Abnormalities Predicting Subsequent Pancreatic Cancer Development, including atrophy, faint enhancement, and duct change, allow for earlier diagnosis. Remember my first slide made the point that we're not doing things well enough? We're not picking it up early enough? Well, this work by Tashima makes the point that we've not always been looking for the right things, that if we look for the right things, they had 100 patients, a little more than 100, that you had pancreatic cancer, eventually proven, but they went back, and anywhere between 6 months and 3 to 4 years, you could find the cancer if you would have looked a bit harder. And so, but it's still hard to do, but I think that's where the computer could take advantage. The computer is better at looking at subtle textural changes. It's better at looking at specific shape changes. It's perhaps as good picking up small duct, and it's good at putting it all together. So as we look for new paradigms, this is going to be very, very important. Most patients with clinical stage 1 pancreatic cancer demonstrated focal pancreatic abnormalities and pre-diagnostic scans at least 1 year before diagnosis. These findings could facilitate earlier pancreatic diagnosis and therefore improve prognosis. Again, this is very important to us because it tells you there's a period of time, maybe 6 months to maybe 3 to 4 years, where we can pick up cancer early in the pancreas. We never thought that, but maybe that indeed is the message. So what's next? We need increased collaboration between the stakeholders: surgery, radiology, medicine, pathology, computer science. We need to have data from multiple sites and varying patient populations, and perhaps federated learning, the subject of another talk, will be critical, and increased collaboration with computer scientists and other non-medical domain experts, but they have the expertise we need. And without the computer scientists and those visionaries, we're going to be stuck in our circle, doing the best we can, but not changing the outcomes. But I think when we can collaborate with people, I think it's going to be awesome. And so with that, I'll leave you with the Donald Rumsfeld quote about the known knowns and the unknown knowns and the unknown unknowns. I think we're trying to decrease the unknown unknowns. There's so much we just don't know. We're trying to make it in our knowledge base and use it in patient management decisions. And with that, I thank you very much for your attention. If you like this video, make sure to subscribe to the CTisus YouTube channel. You can also visit us at ctisus.com for even more videos, plus quizzes, pearls, protocols, and oh so much more. We're also in the App Store and have well over a dozen apps for iPhone and iPad, all completely free. Thanks for watching.